on Tuesdays. So starting from next week, I will do a little quiz on the end for bonus points. So I will just ask you so multiple choice, like 5 multiple choice questions, and then you send the code to my email, and then there is a program that automatically stores the grade. Then the time of seminar, I don't know yet. So in the first week, there might be a different time and than other weeks. Okay. So there is very nice seminarist. There is also another teacher, Maxim Kaledin. I was just talking on Telegram to him, so he confirmed sound. So then grading formula. So there are 3 types of testing: homeworks, colloquium, and exam. Homeworks is deadline is okay, it's 35% for homework, 35 for colloquium. Colloquium is just reproducing theory. I mean, you need to reproduce theory, and then I look in the way how you write, whether you understand it. And if I see you don't understand it, I will ask detailed questions, either to revise my opinion or confirm. And then there is problems exam for 30 points, for 30% of the mark. So then the bonus points, they are added to the final score for the quizzes, and the homeworks have extra questions, and they are added to the score of the exam. So there's like there will be about 6 extra questions, and that means if you all of them have them right, you will start your final exam already with 6 out of 10. And so if there are 5 questions, so if you solve 2 of them, you will have maximal score for exam. Okay. So there is no rounding except in the very last moment that I round final score. Oh, this is on the bottom. I write about rounding. So it will go down if you're less than 5 and up if you're more than 5. So to be in line with all types of requirements. Okay, for homeworks. So there is deadlines every 2 weeks. Sorry, these deadlines, they're not correct. This slide is not correct. The deadline will be every other seminar. So this seminar, you don't have to submit anything for obvious reasons, but in 2 weeks, you need to submit homeworks. And every seminar is a problem list with about 5 problems and 2 homework exercises. And so at every deadline, you submit 4 exercises and you submit them to my email address, and I will grade them myself because I was told there will be about 16 students. So it's not too much, and I can then check what you understood and what not. Okay, so yes. So at the start of every odd seminar, you will need to submit 4 homework exercises. So the deadline is the beginning of the seminar, or let's say half an hour before the beginning, because otherwise everyone is, sorry, some people are like half an hour late on the seminar for clear reasons. They're making homework at home, then they're finished by the deadline and come to the seminar. So, okay, half an hour before start of seminar. Then, okay, colloquium I explained. Exam will be open book, so you can use everything on the wiki plus the main textbooks. There will be 2 books. There is for October and November, there is a book of, I will follow a book of Mori, Introduction to Foundations of Machine Learning. But I've rewritten, hello, welcome. I've rewritten everything so that mathematics is easier to read. Like the guy is from machine learning. He's not a trained mathematician, and they write ugly formulas. And so I tried a bit more, but the material is also tricky. So sometimes there is calculation in the proof, unfortunately. But I think it's much better than in Mori's book. Okay, but I should stay on point. So there are a few other books, and they are in the wiki and the table with explanations and below this table. So the table with course materials. So, by the way, this wiki is very important. So all information I give there, and there is Telegram group, so you should subscribe. Okay, people done that already. So yes, unfortunately, I make a lot of mistakes. I will give lectures on the board, and so you can write on Telegram group if you see mistakes. I will put my phone here during lectures if you have questions. So here is this group here. Yes. I mean, I make little mistakes, but it's actually a good thing. I mean, if there are a lot of little mistakes, it's a bad thing, but it doesn't happen anymore. I apologize to the first year I was here, the students suffered a little bit. The good thing is of small mistakes, you can inform me about them, and then usually discussion starts because, and so there is some interaction. Okay.
Can I please not attend the lecture?
So quiz at the end of lecture.
Not attend the lecture of mine.
Yeah, people who are so if you watch online, you can also attend the quiz because it's just sending me an email. But you need to do it like the deadline is 10 minutes after the end of the lecture. But those in the lecture, they usually write A, B, C, A, and they get the score right away. Okay. So so my laptop replies within 1 minute. Oh, someone is saying something. Can you, is it to me? So Arseni, did you say something? Okay. So Arseni, your microphone is on, so be aware of it. Okay. So what will I do in this lecture? So there are two parts. So first part is technical blah blah, and so practical things I just did, and then now some philosophy and overview, of course, which will be 30 minutes, about 30 minutes. And then the second half, we will start with the course about online mistake model. So the plan is to first explain, so this is called statistical learning theory, but the first 4 lectures, I will not try not to use probability, almost successful. And the plan is that you know all ideas that will be used later in the course in probability-free way, because probability is kind of abstracting, that there is like symmetry and frequencies, and it obscures things. So it's better to just know all ideas, and then you will like this things that are typically difficult, you will have deja vu feeling, like, oh, I already know it, it's easy. Well, if I do it directly with probability, it's really strange what's happening. Okay. So yes, this course is kind of special in the world, because normally there is a course statistical learning theory, and there's a machine learning guy who skips all interesting proofs and then and speak about applications, or there is a mathematicians and he speaks about weird algorithms from statistics and no interesting applications, but he gives all proof with very heavy mathematical machinery. And so what I will do is I will do both applications and all proofs. And for this, I kind of simplified the proof. I cut out all unnecessary mathematics, and just the minimal you need to get to applications. I will be teaching. And then I do the special thing with online learning. I mean, more people do it now, but where you already know all the ideas, and then mathematics become easier. And one of the reasons it works also is because they're pretty good mathematicians who teach you in first and second year. So yeah. So in Europe, like universities, in European universities where I worked before, students like they know all these words, like what is determinant and invertible matrix and things. But when I ask to apply problem solving, it's a problem. I mean, so you actually understand these words, and that's why it's possible here to teach both all proofs and speak about applications. Okay, so yeah. So okay, let's now start. Let us speak about philosophy and outline. So what is statistical learning theory? So the task is the same as machine learning. So you receive some data, and then you have to tell a function that maps some input space to an output space. And so there will be like curly X and curly Y. This will be that's be two non-empty sets. So when you see this letter, always assume it's non-empty. And typically X is finite set or Euclidean space. And in most of the courses, Y will be just a set with two elements because I focus on binary classification. That's also a bit of difference. I dropped a lot of regression stuff compared to save time. So just do something simple, but do it more thoroughly. Okay, and so, well, depending on the structure of Y and how the data is that you can use, there are like four fields. So this is 4 fields in batch learning. Batch learning means that all training data is given right away, and then you afterwards you have to do prediction. And so, but this picture you have seen many times, I guess, in machine learning. So if target is a finite set, it's called classification, and otherwise, so if the training data is labeled and the target set is finite, it's classification. If Y is Euclidean space, it's regression. And if you don't have labels, there is clustering and dimensionality reduction. And so, as I said, we will focus on classification. So clustering, there are some nice applications there, and it will be a few exercises in November. Dimensionality reduction, there is nothing at all, and regression just a little bit. So, because when we speak about neural nets and support vector machines, we are forced to speak about regression. Okay, so then there are other fields. So so in supervised learning, you know, the labels. So we spoke about batch learning, but there was also online learning, which we start now. And so you receive information, you need to make a prediction, you get new information, you make a prediction. So each time you can update the model. And so the goal is to make as few mistakes as possible. That's always the goal. So there is a difference between online learning and active learning. In active learning, you can choose the inputs. In online learning, opponent gives inputs. Then unsupervised learning, you probably heard about. Okay, so you know what is unsupervised learning. Do I need to explain? That's when you don't know the labels in the training set. For example, you get pictures of dogs and cats, but you're not told what are dogs and cats, and you just have to say, okay, I see 2 different animals. So this is clustering. Anomaly detection is just very similar. Okay, Arseni, your microphone is on. Okay. Then there is semi-supervised learning. Okay, I will skip about this to save time. Reinforcement learning, and in reinforcement, so you also have actions that change the problems that can change. So you interact with environment, and so you're solving. And depending on your actions, you're solving basically different different problems of the above type. Okay, what's the difference between statistics and statistical learning theory? So usually in statistics, the inputs have a specific set X. You assume a specific distribution or a distribution from specific family of distributions. and then you want to learn something about it. In statistical learning theory, we try to have no assumptions on X. I mean, it will fail. We will speak about margin assumption, but this is kind of like very general assumption. Okay. So yeah, so opposite of so why should you learn statistical learning theory? Like some people do machine learning and all of their life they're running algorithms, no idea what's happening with how these work, and so you're just typing lines and see some results on some test set, and it some people after some years they find it really boring. And so we do something else. We try and understand a little bit what's happening in these machine learning algorithms. Okay, so you build some intuition, but the course also aims for training mathematical thinking, like it was initially designed for theoretical computer science people too. Oh, I see a message in the chat. Ah, okay. Not, it's nothing. Okay, I see some yeah, so it's also aimed at theoretical computer science people, because some of the things we study here are very fundamental, appear in many areas of theoretical computer science, and I made all proofs completely rigorous. They like this. But last year it was only like 20% of students. I think 3 or 4 students were from there and 16 from other areas. And this year, I think there are fewer students, and maybe nobody from theoretical. I don't know. We will see it. But okay, I'm not going to change the course completely because nobody chose it. Okay, but so you train problem solving and general mathematical knowledge, and then you can like understand articles. So sometimes if you work in a company, they ask you like, oh, we found this interesting article from a conference, implement the algorithm for us. And so then it helps it. And these articles, they start with some theory. And if you understand the theory, you know what so they describe the algorithm, they don't give the source code. But if you know the theory, then little choices are clear how to do it. So, okay, yes. And so if you have like some abstract beliefs, they might be wrong or whatever, it can like initiate research. So if you have certain special belief that something should work in a certain way, it's like there is a story about like some children who are stuck on their boat crashed in the sea, and they go to an island and they don't know what to do for 5 hours until there is a crazy kid, famous for being crazy, and he says that there is a farm on the other side of the hill and everyone should go to the top of the hill. And so he convinces them, and they're on the top of the hill, and then they have nice overview of the whole island, and then they see there is of course no farm, but they see that there are useful like a lake and whatever things, and so this guy saved their life. And so it's a bit with research too, like so certain amount of craziness helps. I mean, sir, look, I need to be careful. There is certain amount. Okay, but I should not be distracted. And so let us just speak about a specific question. So here we will have a classification task, and it will be a rectangle in Euclidean space, unit rectangle are the inputs. And we have two outputs, like a bullet and square. And so we want, and our task, we will receive some data. Here is some data, and we want to make prediction about future inputs. And so we will speak about 2 ways to do that. Let's first fit a half space, and then let's apply one nearest neighbor algorithm. Most of you are in 3rd year, right? Yeah. So it's not yet in your machine learning course, I assume, but maybe you already heard about one nearest neighbor algorithm. Okay, and half space classification, in this case, it means that just we draw a line, and on one side we predict square, on the other side bullet. Okay. And so when we predict half spaces, we kind of take the hypothesis that the true labels are a half space. And so, for example, here is a blue line. It's consistent with all input data, and we can use this blue line for prediction. And so the question is, if the white is the true represent the true label. So every point in the white area is a bullet and black area is a square. So then we see our prediction, unfortunately, is sometimes wrong, right? So there are two regions where it's wrong. So I drawn them here. The black, it's not so visible, but on the left, it's white, on the right is black. So two areas where we're wrong. And so our goal is to somehow make sure this probability of wrong inputs is small. And what's the task here? So there are two things we don't know. We don't know what is the white area, the true labels, and we don't know what is the distribution of the inputs. Maybe so when we so we assume we have some oracle that produces random labels according to certain probability distribution, but we don't know this distribution. Maybe all points are in the top and the bottom of it, but here it's a bit more uniform. Okay, and so then there is a nice theorem. So whoever we draw the blue line, so however we predict, we just need a few examples that are randomly drawn, and then with high probability, we will get an accurate prediction. So here there is a lot of area where things go wrong, but the theorem guarantees that if this area is big, then the probability that an input is in this area is small. And so we will prove this theorem. It's after online learning, one of the first things we will do is prove this. And it's true for more dimensions. So if we have d dimensions, then we just need some constant times d random examples to get the above claim. So with high probability, we get a pretty accurate prediction strategy. But this is only true, this only works if the true labels are actually given by a line. So if the white area is indeed a half space separated by a line. Okay, if the hypothesis is not true, then there is no guarantee. So let us take an example. So here, the bullets are on the second and fourth quadrant. And so in this case, when we fit the line, we will have test error. So if we take a random test point, we will have error at least 1/4. And so there is a nice way to see that we have error 1/4 at least. And so here you see error is 1/2 if we take vertical line. Here also. Here also. Here it's a little bit better, like 3/8. If we use if we predict rectangles on the black area below, you understand. Okay, and so the reason is we can just look at squares with 4 points. So we can see that the input space can be divided by 4 points on a square. And wherever we draw the line, at least one of the 4 points will be wrongly predicted. But to see that's 1/4, sorry, that's 1/4, assuming that we have a uniform distribution of inputs. I forgot to tell. So then it works because we have a uniform distribution over squares. And so wherever is the line, always 1 point is wrong. Okay, so that's about our favorite algorithm to fit half spaces. Like support vector machine is a very popular algorithm. Like if you want to fit half spaces, neural nets is completely overkill. But just or whatever linear regression model, not regression, but linear class. Yeah. So Okay, so now let's go to nearest neighbor algorithm. So what is this algorithm doing? So given a certain point, it will predict the one nearest neighbor algorithm will predict, will look to the training set and choose the input that's closest to this point and predict the same label. So k nearest neighbor will look to the k closest points and take majority, but we just need one nearest neighbor. And so the prediction strategy you can find by looking to the line in the middle of 2 points. I don't know how it's said in English. Like in primary school, they speak about it, but it was in Dutch. And then, anyway, these regions are called Voronoi regions. So every cell is the area where a certain point is closest. And so this is really cool classifier because when you make predictions, you will never be wrong on the training set. So this is kind of rule. If the test point is equal to sum of the training points, it will always be right. But moreover, this can approximate any classifier. So any true shape of white, you can you can generate points according to any distribution. And if you have enough points, this one nearest neighbor algorithm will make perfect prediction. So it looks like it's perfect classifier. It can fit anything, and it never makes mistakes on training set. And so one would expect that just in almost advanced classifiers, why not use one nearest neighbor algorithm? So maybe some of you know, why shouldn't we use? Yeah.
Probably because we will need like a lot of data, unrealistically many points. So it is just like impossible to do in practice.
Yeah. So the tricky part is that indeed, if we have enough inputs, then indeed we will converge to the true classifier. But this convergence is extremely slow. We need a huge data set. Okay, and that means that in statistical learning theory, we care about like how fast the test error converges to 0. And then there is this question: why does one nearest neighbor and algorithm converge slowly? Well, first, if you're in 2 dimensions and the decision boundary is like smooth, then it will converge quite fast. But so there are 2 assumptions, like smooth decision boundary and 2 dimensions. For large dimensions, the problem appears. So here I made I made a theoretical counterexample, and then I did some simulations. So let's take as input space a d-dimensional hypercube. So just so the inputs they are vectors with coordinates -1 and +1. And we add one more point in the center. Okay, and the point in the center will be positive and will be a square, and all other the points on the corner of the hypercube will be squares, and the point in the middle will be a bullet. So then we can check one nearest neighbor algorithm, and we will see that probability that a random test. So we can. Okay, let's even make the problem more easy. Let's take a distribution, a simple distribution on the inputs. Like with one, so the point in the middle has probability 1/2, and the other points also have probability 1/2, and they are uniform. So so the inputs, so sampling an input is as follows: we flip a coin. With 1/2, we take the middle point, and in the other case, so if heads, we take the middle point. In the other case, we flip again d coins, and we pick a random point, a random corner of the hypercube. So that's distribution. And then let's apply one nearest neighbor classifier. So first we generate a training set according to this distribution. We will say, we will take n points according to this distribution, and then apply one nearest neighbor algorithm. And then we see that probability to be correct is 1/2 plus n times exponent minus d over 2. So that's maximal probability, this upper bound on probability to be correct. So what does it mean? So if d is equal to 30, for example, or let's say d is equal to 100, probability will be exponent of minus 50. So n times exponent minus 50. Exponent minus 50, it's really small. So you need billions of inputs before you can extract the correct pattern. So in this case, nearest neighbor algorithm is just equally effective as random guessing. So it doesn't learn anything at all. Okay, and this is kind of special geometry. I did a second experiment. So let's take a case where the classifier is a half space. So let's look to the, here is again points on hypercube, but without the middle. Sorry, points, but not the inside of hypercube, not the corners. And so I classify according to the first coordinate. If it's positive, I say square, otherwise I say bullet. And then I look to, like in the right of the graph, there is size 100. And then at this dimension, error of one nearest neighbor algorithm, error of one nearest neighbor algorithm is like 0.35 for 10,000 size, training size 10,000. So you see that in this case, test error remains quite big. Even the true classifier is some simple linear classifier. But then SVM is an algorithm, we will learn about it. It's very popular algorithm like 15 years ago, 18 years ago. And so if we run it on this problem, then the error will be astronomically small, even in 100 dimensions. So this algorithm just fits hyperplane. And so why is this happening in this problem? Because it's very simple problem. We just have hypercube, and we take a random point in the inside and classify according to first coordinate. So the problem is that the 99 other coordinates, they are noise. So they're random numbers between 0 and 1, and this noise becomes Gaussian, proportional to square root of the dimension. And so this noise will overpower this first coordinate and give some information. And so that's the problem why one nearest neighbor algorithm doesn't work. So there are a lot of coordinates with noise, and they overpower the useful information in the distance. Oh my God, I forgot to put charger on my computer. Yes. I need to go faster. Okay, so what we conclude from this, if true classifier is indeed a half space, then fitting half space, you get a good approximation with a number of samples proportional to dimension. But if it's not a good classifier, if half, but in general, if true classifier is not a half space, it can be exponential. Okay, and so here to make it more to give an easy explanation, I changed the input space. Instead of inside of hypercube, I used again corners of hypercube. So I used binary inputs this time, 0 and 1. Okay, and the result, it's a little bit better for one nearest neighbor algorithm, but still very slow convergence after 10,000 training size. And now we have something nice because in statistical course, you have, so what is happening now, every feature is Bernoulli variable. So every coordinate is random Bernoulli variable. And you know that if you add random Bernoulli variables, you quickly converge to normal distribution, right? So we can kind of understand this. And there is another bound called Chernow bound, and we can use it to prove something. Okay, so oh, by the way, so this is again the example. Yeah, okay. So but did I prove something? I forgot. Ah, no, I didn't try to prove. Okay, it's a bit difficult. Yeah, okay, so this is not a theorem. It's just like informal explanation that okay, let's skip it because it's not so convincing and running out of time. So by the way, this is illustration. If you add up Bernoulli variables, it's like a famous Galton board. If you add up Bernoulli variables, you approach a normal distribution. But here we use that so in one nearest neighbor algorithm, there is a one coordinate that's informative, but the standard deviation goes up with square root n. So what we have is two normal distributions that are very wide, but one label, the distribution for positive labels compared to the distribution for negative labels, they're just shifted by one unit. So just by one, in this picture, you see all bags. There's just shifted by one bag. And so you see that accuracy on prediction will go down by 1 over square root of the dimension. So the probability, so the more dimensions you have, the maximum you can hope for, and the prediction accuracy, the more you can hope for. Deviation from 1/2 will be 1 over square root n. Okay, but I'm not speaking clearly. Probably you can understand me. So there is a distribution for one label, a distribution for another label. And so if these distributions are non-overlapping, you can make pretty accurate predictions. But if they are almost identical, then you cannot predict very well. And so prediction accuracy or the prediction error will be 1/2 of the overlapping area. But here, the overlapping area, if you just shift by one bag, it will be exactly the maximal height of the bag in the middle. And this height is 1 over square root n, if you remember from statistical learning theory course. So what I'm saying now is some advanced things. It's not essential for what I'm telling later. So now let's quickly speak a bit about philosophy. So, okay, so what's problem with overfitting? And so I will explain it with some scamming technique. So there is football tournament, and there are 20 games. And before the tournament, so imagine that, okay, everyone listens, looks to this tournament, and you're checking your emails, and some random guy sends you an email with prediction for the first 10 games. And so you watch this tournament on television, and after 1 month, you see that his 10 predictions are right. And then you receive a new email. He says that, okay, I can sell to you the next 10 predictions for 1 ruble. And so imagine that you live next to gambling house. And if next 10 predictions are correct, then you can turn 1,000 rubles in more than 1 million rubles. So that's kind of like small investment on your side. But then you just have to send 1 ruble to this guy. So would you do this? So I know you already checked the slide, so but somebody else. So can you switch on microphone or say something? Would you do it? Yes or no? This first question.
No,
No. Okay, and why you will not do it?
I don't send my internet by
Okay, but imagine okay, yeah, no, internet is important, yeah, but imagine, okay, so he asked for Bitcoin transaction and you're used to paying with this and it's safe, uh, so yeah, I'm trying to okay, is there other people, other reactions? uh I mean, with a more mathematical argument than just it's a bit difficult in this example to change internet. Uh, uh, well, okay, there are other examples like people that predict your future. So imagine that you go, some people, they pay money and then some guy do some magical things and tell you you will have so many children and so on, and then you will die at this age and so on. There's simple, okay. So let's now say that, okay, a friend comes to you and he tells to you like, I want to warn you about scam from email. He says that there is a guy and he sent me email also with predictions, but then I tracked this guy and he was basically sending emails to 1024 different groups, and each group he sent different predictions. And then after in the middle of the tournament, after 10 games, he only sent follow-up mail to the group that received correct predictions to ask for money for next 10 predictions. And so if you know this information, then usually people say, no, then I will not pay 1 ruble to this. Okay, it's still streaming on YouTube. So hopefully the sound okay. Maxime. Yeah. Okay, you can continue. So, okay, so what would be more credible if there is like a famous company, whatever, Yandex.com, and they publish like a list of 20 predictions for the 10 games. And then you think, okay, that's 20 out of 10,000 of thousands. And then maybe you want to pay 1 ruble for next 20 predictions in case one of these 20 are correct. So that's more real. I mean, this might be more value. And then you can go in the gambling house and then distribute your money on 20 predictions out of 1,000. And if opponent chooses 50-50, then you can turn increase your money, seed money from 1,000 to 50,000. So it's credible situation. I mean, you can hope it can still fail if Yandex makes a mistake. Okay, I don't think that Yandex is in gambling business. It's just the first example that pops up. Okay, so that means that if we limit our hypothesis space, and if one of these hypotheses is correct, then we might have confidence in the future. And so all of this course is to understand when can we have confidence in the future when we have good predictions on training set. So in machine learning, this is okay. So in machine learning, there is cross-validation, but the problem is that there's too many things you need cross-validation for, and it's very expensive. And so that's one of the places where this kind of excuse of statistical learning theory as practical application. But the real motivation is to understand what is happening inside machine learning. Okay. So, okay, in machine learning, we don't have just predictions, we have certain models, and for example, decision trees. And decision trees that are very large, they can produce any model, basically. But if we can find a small decision tree that predicts the training data well, then we can have confidence in our trained model. So that's like first message of statistical learning theory, that your model needs to be small. But like small sometimes counted a number of parameters, but that's kind of naive interpretation. Because in neural nets, it's the more parameters, the better. But the thing is, so one of the goals of this course is to explain that under the hood, something strange is happening, this gradient, the stochastic gradient descent with random initialization. And there, basically, some small class of hypotheses get huge preferences during training. And so the same principle applies, but it's in some weird way it's applied. So in some transformed way, you're doing what SVM is doing. It will be one of the conclusions of this course. And so the same theory applies there too. Okay, so this is what I'm saying here. So so one way to explain it is to say that in neural net, simple solutions, they have many symmetries. They can be encoded in many different ways in the network. And so if gradient descent basically picks an over-parameterized regime, basically picks a random consistent solution. And since simple hypotheses have appear many times, you are more likely to pick one of them. It's very high level overview of what's happening, and it's one of the ways to explain it. And yeah.
So the point is that over-parameterized neural nets not like overfit, but opposite gives better solution simply.
Yeah, it gives a simple solution, but it doesn't look simple because it fills all your hard disk with numbers. But in a mathematical sense, it picks something special. But but the theory of neural nets, it's just from last 5 years, so it's a lot of gaps in this theory. And so, okay, I will soon. Okay, there is more philosophy about productive learning, but I need to skip this. Mm, okay, and so what will we speak about? We will speak about people in machine learning call it bias variance trade-off. So if you fit an easy model, then you might have some bias, like when you do linear regression, linear classification, like we did. If the decision border is not a small line, you will be wrong because you deviate from the true line with your too simple line. On the other hand, if you follow a very complex hypothesis, then you might have no reason to have confidence in it. If you generate new training data, you will have a completely different model with completely different predictions. This is kind of bias variance trade-off in machine learning, and here it's called like bias complexity trade-off. And so some people call it like this in statistical learning theory. And so what we are doing is we will make a bound on the error of test set. So we assume data for training and testing is generated by same distribution, and then we make this bound, and this bound will be a sum of two things. So it will be error on training set plus some overfitting term. And so when the model is very complex, overfitting term is large, but the bias is small. The error, the best error of the model you can train. If you have infinitely many data, you can select the best model, and this will have small errors. So that's in the blue, error on training set. And then in red is overfitting term. And so bound is a sum of the two, and here is excuse of statistical learning theory. Like you can avoid fitting hyperparameters by cross-validation if you plot the curves for your parameters and then select the parameters in the sweet spot in the middle, where the error on test set is guaranteed to be small. Okay. And so then in our so boosting and SVM, they used to be very important. Like for a long time in machine learning, they were actually better than neural networks, unless the person is really professionally trained, like full time for 5 years training neural nets. They get like magical, and they can reproduce anything else in a lot of applications. But in the history, like for normal people, SVM and other boosts have been like alternating the best, like first SVM, then various boosting out, gradient boosting, and so on. And so we will argue that implicitly these algorithms optimize such a curve. And then, okay, so and yeah.
About this plot. So optimizing these bounds, as far as I understand, also implies that we need to learn like a lot of models. So it's like pretty the same as cross-validation.
Yeah, yeah.
So what's the practical optimization of this model?
Well, there are theoretical ways. Okay, so in SVM, like you're doing the same thing, but you will see that the curves. Okay, so in SVM, there's still hyperparameters, but you transform this curve with a sharp minimum to one with a very soft minimum. And then you see that choosing the parameter C is not important. And what you say is trade-off somehow implicitly happens inside the algorithm.
This is a lot of the theory.
Yeah, yeah. And in other boosts, it's also implicit, so something implicit is happening. Okay, for other boosts, their margin assumption and Okay, so that's why I say I will not prove it is, but I will say I will argue that somehow, in some sense, it is empirical risk minimum. So it's very careful conclusion. Uh, okay, so overview, of course. First 4 lessons on online learning. So today, halving algorithm and hopefully perceptron algorithm if things, oh my God. Uh, um, then 4 lessons, we will do like core theory with probabilities. So what is it? So we will determine this overfitting term in the next 4 lessons using something called Rademacher complexity. And then in the next 4 lessons, we apply it to SVM, AdaBoost, and neural nets. And then the last lesson, I will try to explain about recent theory, but I not finished preparing them. So I will try to explain a book that appeared 1 year ago, like the main conclusions and main ideas of this book. But it's a difficult book. It's called Foundations of Deep Learning by Roberts and Shaida. But I am not sure if I will manage to read and simplify everything so it's accessible. But this is yeah, explanations for why neural nets work very well. And so there is a first level of explanations that connected to SVM or support vector regressions. But there is also a deviation from this old algorithm. And so this book tries to explain this deviation, make a mathematical model for this explanation. But okay, this is tentative. Otherwise, I explain something else about a double descent. So double descent is like this curve. So when the complexity, so when we look to gradient descent in neural nets, then we can associate complexity with number of parameters, the width of the net, basically. And we see that if we keep increasing the width, then at some point it starts to go down again. This is called double descent phenomenon. And people nowadays always train in this after the second step. This is called over parameterized regime. So number of parameters is like 10 times more than number of, I don't know what is the factor, but as I understand, it's like 10 times more than the number of training samples or whatever, certain factor more. Okay, and so that's what is very interesting theory. But okay, this theory is full of gaps and strange things and things that are not discovered yet. So, but okay, I will give you the best explanations I know in 3 months, because that's for December. It's too, I will make the lessons optional because they're not yet fixed and it is a bit dangerous. But students next year may be mandatory if I teach it again. Okay, so now let's finally, in the last 20 minutes, let's speak about online mistake model. Okay, so now no probabilities this lesson. And so, okay, I will skip the overview. So what's the problem here? So there is a problem in the classroom, and now solved. So long time ago, I was organizing activities for children. So I looked at Wednesday, I have to say we will do this. And then Saturday was activity. And I need to choose indoor, outdoor, depending on the weather. So when it rains, it had to be indoor, otherwise outdoor, because children were unbearable indoor. They were very energetic. Okay, and so I learned about the weather and alternate between learning and suffering some consequences of my decisions. So the more I suffer, the more I learn, basically. So and then I mean they're nice children, so somebody sees it. Just at the age or 8 or something, 8, it's children have all male with a lot of energy. Okay, so that's what we will do. And so I will now explain this game. And so it will use a hypothesis set. So recall from philosophy discussion, we always need to fix some set of predictors. And we need to promise that one of these predictors will be right in the labels we receive, for the labels that we receive. But in advance, we don't know which one is right. That's a problem. So I model it as a game. Wow, people in this field always do. Two players, predictor and challenger. And so they both know a set of hypotheses H. So H is function from inputs to outputs. X always inputs, always non-empty. Also H is always assumed to be non-empty. And so it works as follows. Challenger selects a hypothesis from H, so a classifier. So Y will always have two elements. I will speak about classification in the next 4 lessons. So Y two elements, rain or sunny, for example. And X, I look to the clouds, look to the date, look to historic weather reports, look to now weather reports, and draw conclusion. So that are inputs. And so for increasing T, so then there will be rounds. In each round, challenger gives me some input. And then I need to make a prediction. And then challenger, and then there is some supervisor. He does not do nothing except some practical things. He will tell me if I made the right prediction. And so if I'm wrong, then I can use it to update my model. If I'm right, I can also update my model for the next round. Then I make a new prediction. So is it clear? So just 3 steps. I receive information from challenger. So imagine I'm the predictor. I receive information from challenger. Then I make a prediction. Then I learn whether my answer is right or not. And then I repeat again. And my goal is to make a minimal number of mistakes. Okay. So, and then this challenger, the classifier chosen by challenger is sometimes called the true classifier. Okay. So let's do an example. So a strategy for, so first, let's say that some simple set of classifiers, which are, so the inputs, okay, in the class, you cannot see it, it's just binary strings of length n. And then the classifiers are projections on coordinates. So the first classifier will project on, will return the first bit of the word, of the input word. So it's clear because some people are looking unhappy to me. So inputs are bit strings of length n. There are n classifier in H. And each class, so the labels Y are 0 and 1. And the classifier is just projection on the Y coordinate. So for example, F1 is just the first bit of the input word. Okay, and so now let's consider algorithm. It just, so let's make a list of all the projections F1 till Fn, and algorithm will look to all input-output pairs we have received in previous round and select and will believe the first classifier that's consistent with all these pairs. So let's do an example. For in the first round, we receive the input 0, 1, 0, and then we will predict according to F1 because we have no input-output pairs yet. So all of them are correct, and F1 is the first in our list. Okay, then that means we predict 0. And now for the case of example, let's say that opponent choose the third classifier as the true one. So I put n equal to 3 in this example. So input space is bit strings of length 3, and then so we are right. So the predictor tells us we are right. Okay, there's a small mistake. I'm just supervisor tells us whether we're right or not, but since we have binary prediction, it's the same thing. When we have non-binary prediction, it's something different. So there is a homework exercise maybe that you will play with this, or seminar exercise. Okay, the next one, imagine Challenger gives us 1, 1, 0. Then we will again predict according to F1 and say 1, but now we are wrong. So now the list of consistent classifiers at this point is only F3. Okay, and that means from this point on, we will always predict correctly. So in this run of the game, we made one mistake. It's clear? So what's the model? This is an example of algorithm. And so we can do this algorithm more generally. You can do it for each age that's finite. And so just, I may prepare the question. So just think about general dimension. Before we had n equal to 3. Now let's think about general dimension. Oh, this is the answer. So what's the worst case number of mistakes for general n? Yeah, n minus 1, because yeah. So each time we make a mistake, so let's prove upper bound. Worst case, we can make at most n minus 1 mistake, because each time we make a mistake, we need to drop at least one classifier, the one we were using for the prediction. And now let's make the lower bound. So can we imagine scenario where where this algorithm will make n minus 1 mistake? And this here is example. So we just give 0 followed by all ones. And so true classifier looks at the last bit, but we will predict in the first round, we predict 0. And we always predict 0. We're always wrong until round n. Starting from round n, we removed everything. Okay. So, but this is for specific classifier. You can do it for all classifiers. You can prove that you make at most, if there are k classifiers, at most k minus 1 mistake. Okay, this is easy, but we can do better. So we can, so let us define m of h, the smallest number for which we have. Okay, so it's the smallest number m, such that predictor has a strategy in which he makes at most m mistakes. So this h, so capital M of h, the smallest number m, such that we have a strategy to make at most m mistakes. And so previous theorem proved that m of h is at most size of h minus 1, assuming h is finite. Okay, that's clear, I assume. But we can do better. We can get logarithm of the size of h. And so you know how. You already know with the other. So x, we can divide yeah. Predictions. Yeah. Yeah. So we use binary classification and we choose it's called majority algorithm. So we look to the set of consistent classifiers, and then we take majority vote of them. And so either majority vote is correct, or when it's wrong, it means that the set of consistent classifiers decreases by half. In other words, at each mistake, we lose at least half of classifiers. And that means that a number of mistakes is bounded by logarithm of size of hypothesis class. Okay, and so this full proof. So I forgot to like define. The set of consistent classifiers, it's so important. It's called version space. It has special name. and the field. Okay, so this is like there are six little presentations I put together. So in this first part, we defined online mistake model and proved halving mistake upper bound of logarithm. Okay, so now let's speak about necessity of hypothesis class. Imagine we have no hypothesis class. Then there is a way, if we receive finite age, then there is a way to get to always get log age. If h is finite, maybe that's okay. But sorry, if x is finite, that's okay. If x is infinite, we can have infinitely many mistakes. So imagine x is infinite and we have the class of all classifiers on x, then our m of h will be infinite. And so how can we prove this? So input space is infinite. I claim that Challenger always has a strategy to make us always run when h is the set of all classifiers on x. Okay, so let us say that x is just natural numbers, 1, 2, 3, 4, and so on. And Challenger will just give subsequent numbers. And then, but we also have to say what is true classifier that Challenger will give us. And to do this, Challenger will think about the prediction strategy. And he will just look at these inputs and then choose as label always the opposite label that predictor makes when he runs the game. So do you understand? So now predictor is thinking, and predictor has seen the algorithm of Challenger, and so he just runs in his head the strategy, but on the input 1, 2, 3, and so on, all different inputs. And then he receives labels for these points. And now he can win the game because we said that h contains all functions. So there is infinite function and it must belong to h because h has all functions. And so Challenger will say that's the function, that's a true function. And then predictor is always wrong on this function in this game. So it's pretty easy. Okay, that's what I explained here. And so that means that with infinite classes, infinite class, we always need to restrict h, otherwise we cannot have finite mistake bound. And so the same thing in machine learning, people say no free lunch theorems, and they write like refer to long papers, but it's just a simple idea what's happening. And so we will do something similar later. Okay, so basically the message that we see over and over again, if we don't restrict h, we have no meaningful guarantee on error during testing. Okay. So here I repeat again, set y will always be for a long time, will always have two elements. And x, y, and h are always non-empty. So I will not write this. Okay. So now, okay, this is kind of very artificial model, but the same thing actually happens with half space classification and online mistake model. And it already happens in one dimension. So I'm gonna skip it because of time. We should learn something else too for seminar. Okay, so this is skipped. Then counting decision trees, I will ask a seminarist. Okay, that's so here you see. So let us apply this to decision trees. And so the decision trees whose inputs are binary strings. And so the number of decision trees. So you know what is decision tree? One person. Oh, sorry. Yeah. Okay. Okay. Yeah. So so decision trees, and so number of decision trees on n-bit inputs with k nodes is bounded by this formula in the bottom, n plus 2 to the power k. So this is a nice formula, and so we can apply it to halving algorithm. And so there is a nice conclusion. If we want to train decision tree an online mistake model, we will make at most k log n plus 2 mistakes. So that means number of mistakes is roughly proportional to the number of nodes in the decision tree. Okay, and so how it works, we just apply algorithm. It's a completely unpractical algorithm, just application to make some connection with machine learning. So why is completely unpractical? Because to check all decision trees, your algorithm is very slow, like n plus 2 to the power 20, for example. And so if you want to learn decision tree of size 20 on 14 inputs, then you will have at most 80 mistakes. That's what formula is saying. But fortunately, number of such decision trees is like 16 to the power 20. It's way too big. There's many billions just for one prediction. Okay. So, but there is also another thing, like when we apply a halving algorithm in this way, we need to know the k, the number of decision trees. So we can we can make an algorithm that does not need to know k. So how does it work? Well, first is naive way. So what is naive way? We start with decision trees of size 1, for example. And then we train until no decision tree of size 1 is consistent with the data. If this happens, we restart training, but now with decision trees of size 2. And so we look at the errors. And we know that to get through one set, we need roughly proportional to k many mistakes. So if there is some, so if the smallest decision trees that is correct has size k, we will make k squared mistakes with this naive approach, right? So we need to make at least, so in our upper bound, we can happen that we make k log n plus 2 mistakes to make to make one iteration of our algorithm finish. So actually we need one more mistake. So as long as one decision tree is consistent, we're guaranteed to make at most k log n plus 2 mistakes in the route. We need to make one more mistake to completely empty this hypothesis, because at each mistake it can happen that just halves. So that means we get quadratic bound in k. But we can do better. And so we can somehow combine all the rounds. And the plan is now to every decision tree, we will assign a weight and take weighted majority algorithm. So we will assign weights such that the sum of all weights of all decision trees is at most 1. And we know that at each mistake, the weight of all decision trees in the version space will halve. And so that's how we get a quite nice result. And so without knowing the price for not knowing k will be the error bound we had when we knew k plus just 2 log k. Well, 2 log k plus 1. Yeah. So this is very small, like if k is 20, 2 log k is plus 10 more mistakes for not knowing k. If k is even much bigger, it's more impressive. So if k is 1 billion, that is just okay. So this is very impressive, and I already explained how it worked. So we just we update weight, but there is again a part where I assign the weights. There is a part missing in the algorithm where I define version space and update the weights. No, the weights are fixed, sorry, for every classifier. Oh, so yes, okay, and if this version space in the sum is clear, then that's correct, sorry. Everything is okay. So is algorithm clear? Because it doesn't look, some faces aren't happy, so say something. Okay. So let me say it again. So let's quickly look to, no, it's too many slides. Okay, so what we see here, we receive some input, and then for making a prediction, we look to all class. So I look into the bottom of the slide. To make a prediction, we look to all classifiers in the version space. And we will take a weighted majority algorithm. So and now I need to explain this. For labels, I will use -1 and +1. Okay. Yeah. So what we will get if the classifiers that predict +1 have more weight than classifiers that predict -1, then the sum will be positive. Okay. Yeah, weights are in initialization, so it isn't in the middle of the slide. So the weight is defined to be 1k times k plus 1 times 1 over the size of each. Okay, it's yeah. So basically, it's the weight for the pair fk, and here I should sum over pairs fk in the version space. So this is minor mistake. Well, to you, do I say? Okay, so now algorithm is clear. You can implement it. Okay, and so now I claim that a number of mistakes is bounded by this thing. And this is easy to see because the quantity in the theorem is precisely the logarithm of this thing. So what's happening? Initially, the sum of all weights is 1. So that's why I choose the strange weight. So when I sum over all classifier in a class, then the second term in the definition of weight becomes 1. And then when I sum over all k, there is like nice formula. I should check it. I will skip it. But the sum over 1 over k times k plus 1 over all k equals 1. So the sum of all weights is 1. And so then if there is a true classifier, this true classifier will always be in the version space. So weight of true classifier will be a lower bound on the weight of version space. And at each mistake, weight of version space halves. Okay, so number of mistakes is at most logarithm of weight of true classifier. In fact, it's the sum of all weights of classifiers that are always correct. Because in decision trees, you have redundancy. So if you're lucky, like for different case, you can find more. So the lower bound might even be a bit better. I think I spoiled homework exercise now, but it doesn't matter. Okay, so I guess I need to stop. Oh, here is the proof, but it's better if you do it without formulas. And so here are conclusions. Okay, so in beginning of seminar, I will ask, I forgot his name, Arthur, to speak about weighted majority algorithm, and maybe about perceptron algorithm. Okay, and then the class is finished. So see you next week. Yeah, see you. Bye.